Okay, let's dive right into a fascinating cosmic detective story. For centuries, we've stared at our sun, we've studied it, but there's this one huge, fundamental question that's always been a mystery. Where did it actually come from? It's a bit of a cosmic cold case, right? We know so much about our sun's life, but its childhood home, the stellar nursery where it was born alongside thousands of siblings, well, it's missing. You gotta understand, stars aren't born in isolation. They form all together in these big, dense clusters. But over billions of years, the galaxy's gravity and just motion, it pulls these families apart. So our sun is basically an orphan, and finding its long-lost siblings is one of the great puzzles in astronomy. But there was a lead, a prime suspect, located about 2,700 light-years away in the constellation Cancer. This is the open star cluster known as Messier 67, or M67 for short. And you know what? For a long, long time, it looked like the perfect match. So why M67? What made astronomers so convinced that this specific cluster, out of all the clusters out there, could be our sun's long-lost home? What made it such a perfect candidate? Well, the circumstantial evidence was incredibly compelling. First off, the age. M67 is about 4 billion years old, which is amazingly close to our sun's 4.6 billion. And, crucially, its chemical composition, what astronomers call its metallicity, was almost identical. See, stars born from the same cloud of gas should have the same chemical fingerprint. So M67 had the right age and the right DNA. On paper, it was a perfect match. So to really investigate this suspect, the astronomers, first needed a definitive list of who was actually part of the M67 family. You have to know who was at the scene of the crime, so to speak. But this is a lot harder than it sounds. Looking at a star cluster is kind of like trying to take a family photo in the middle of Times Square. How in the world do you tell who's part of the family gathering and who's just a random bystander photobombing the shot? You've got to somehow separate the real cluster members from countless stars in the background and foreground. And this is where modern astronomy completely changes the game. Instead of painstakingly counting by hand, scientists can now unleash this incredibly powerful tool, unsupervised machine learning. They basically feed these algorithms massive data sets of star positions, their movements, their brightness, and then ask the computer, find the stars that are moving together as a group. Go find the real family members. So, by applying these amazing algorithms to the incredible data from the Gaia Space Telescope, scientists finally got a clean list. They were able to confidently identify 1,422 stars as true, bona fide members of the M67 family. At last, they had a reliable roster to work with. Now that they had all the family members identified, astronomers could create a proper family portrait. It's called a color magnitude diagram, and it's a really fundamental tool in astronomy. It plots each star's brightness against its color, and that tells you exactly where it is in its life cycle, from the hot, bright young stars all the way to the cool, bloated red giants in their old age. And this family portrait revealed some oddball relatives. They're called blue stragglers, and they're stars that look way younger and bluer than they have any right to be in a cluster this old. They're probably the result of stellar collisions or mergers, and their presence tells us that M67 has had a very dynamic and probably pretty dramatic past. Okay, so we've got the family members identified, we've seen the family portrait, now it's time to run a background check on the prime suspect's history. Investigators needed to trace M67's path back through the galaxy to see if it ever actually crossed paths with our sun. So, scientists ran hundreds of thousands of orbital simulations, basically rewinding the clock on the sun and M67. And the results? Well, they delivered a bombshell piece of evidence. No matter how they ran the numbers, any encounter they could have had in the past would have happened at an incredibly high speed. This plot here shows you one of those simulations. The sun's past orbit is that thick line, and M67's is the thin one. You can see it right away. Their paths are wildly different. For our sun to have escaped M67 and ended up where it is today, it would have needed to be flung out in a really violent, high-speed ejection. And here is the smoking gun. An ejection at over 20 kilometers per second is so violent that it would have completely shredded the delicate disk of gas and dust that was trying to form around the young sun. In all that chaos, our planets, including our own Earth, would have never even had a chance to form. And with that, the case is closed. The evidence is crystal clear. M67 has a rock-solid, airtight alibi. As compelling a suspect as it was, it's innocent. But wait, just when you think the story is over, there's a really fascinating twist. M67 might not be our son's parent, but it turns out to be something just as valuable, maybe even more so. This leads us to this powerful concept called the solar-stellar connection. The whole idea is that the best way to understand our own star is to study its twins. And M67 is an absolute treasure trove of hundreds of stars that are almost exactly like our sun, all conveniently at the same age and the same distance from us. And this is what that science actually looks like. These graphs are called light curves, and they're tracking the brightness of those solar twins in M67. You see those regular dips? Those are caused by dark star spots rotating in and out of view. By measuring the timing of those dips, we can figure out exactly how fast each star rotates. And that data is absolutely critical for testing our models of how stars like our sun live, evolve, and age. M67, as it turns out, is the perfect solar laboratory.
So, after all of this entire cosmic investigation, what's the big takeaway? What have we learned?
Well, this is just a perfect example of the scientific process at its best. The idea that M67 was our sun's home was a fantastic hypothesis. And even though it turned out to be wrong, testing that idea led to incredible new tools, like using machine learning to map out star clusters. And it gave us a much, much deeper understanding of both M67 and our own solar system. So the mystery of the sun's birth, it remains open. Its lost family is still out there, wandering somewhere through the Milky Way. But this whole investigation has sharpened our tools and our focus. It really makes you wonder, right? With even bigger telescopes and smarter algorithms just around the corner, what will it finally take to crack this ultimate cosmic cold case?